Okay, we want to start thinking about how do we get a computer to do things for us. So we can start by saying, well, what do we want a computer to do? We want it to compute something. Sounds like a deep philosophical question. And in fact, it is, and that leads to an even deeper philosophical question, which is if we want a computer to compute something, we can ask, well, what's the knowledge that it's going to use to do that computation? And that actually leads to an interesting distinction, because we can divide knowledge into two types, what we're going to call declarative knowledge and what we're going to call imperative knowledge. Declarative knowledge, those are statements of fact, statements of truth. For example, if I were lecturing here at MIT, I might have gone in ahead of time and strapped some or taped some candy under one of the chairs inside the lecture hall. An imperative piece of information simply says, there's candy taped to the underside of a chair. It doesn't tell you anything about how to find it. It doesn't tell you where to look for it. You'd either have to do it in parallel by having every student reach under the chair or search the entire lecture hall. It's simply a statement of fact. Imperative knowledge is a recipe. It's how-to knowledge or how-to information. And this gives us a sequence of steps to find a solution. Again, if I stuck candy under a chair inside the lecture hall, I might say to the lecturer, do the following. Face the students at the front of the room. Count up 1, 2, 3 rows. Start in the middle section, left side, go in one chair. Look underneath it. Candy is there. It's a recipe. It's a sequence of how-to steps, very mechanical, to get things done. Those two kinds of knowledge are important, but only the second one's going to really be of value to us, because that's what's going to help us get the computer to do something for us. To see it, let's look at a simple example. Suppose I want to compute the square root of some number. To make it easy, I'm going to start with just an integer number. Here's a statement of fact. The square root of the number x is that y such that y squared is equal to x. And I'm just going to highlight it right here. There it is. There's a statement of fact. Does it tell me how to find a square root? No. If somebody gives me a good guess, I can use this to check. So if I'm trying to find the square root of, say, 16, and somebody gives me a guess of 4, I'm lucky, because I can say 4 times 4 is 16, and I'm done. But it doesn't help me find something. Here's a version of imperative knowledge. And this is actually a very old algorithm. It's attributed to Alexandria of Haran, dating back into the 2nd century BC, although other people suggested it existed earlier than that. But here's a recipe for finding square root. I'm going to start with a guess, and I'm going to call it g. If g times g, if g squared, I'm going to go back. If g squared is close enough to x, then I'm going to stop and say g is the answer. Otherwise, I'm going to create a new guess by taking g and x divided by g and averaging them together. Take the average. Okay? Once I've done that, I'm going to repeat. I'm going to go back up and do the same thing again. And that's going to give me a little algorithm, because it's going to let me now say, start with a guess, check to see if the guess is close enough, and if not, keep going. And you can see that at a little graph at the bottom. I start with not a very good guess. G is equal to 3. I square it. That's 9. 9 is not, as you can see here, very close to 16. So I'm going to take x divided by g, which is right there, and I'm going to take g, and I'm going to average them together to get a better guess, right there. With that better guess, I'm now going to do the same thing. I'm going to go back through that loop, go back up to step number 1, and say try it again. And you can see the steps here. I square 4.1667, I get 17 and change. It's really not close enough. I take x divided by g, I take the average of x and x divided by g, and I get a much better guess. And you can see after the next round, I get a guess that's close enough, I'm probably ready to stop. So, this is a nice example of a little algorithm. It's a little recipe. And let's capture those pieces together. What's a recipe? 3 pieces. It's a sequence of simple steps. It's a flow of control, a process that's going to tell us what order in which to execute the steps, and it's going to give us a way of deciding when to stop. So those 3 pieces, simple steps, a sequence of things I want to do, a checklist. A flow of control, a thing that tells me when to go to the next step, when to jump to some other place in that sequence of steps, and a way of deciding when to stop. Those three pieces constitute an algorithm. And you just saw it in the little square root example. In general, the flow of control was going successively through the steps until I got to a test, and that test had me jump back to another place inside the algorithm. That's what an algorithm is. That's what a recipe is, and that's what we want to capture.